So this video is on homework on the second night of volumes with known cross section. So we're just continuing that lesson, and in 1D we have a solid that we're going to create in the shape of rectangles, and the equation of the circle or the base or the plate, however you want to think about it, is x squared plus y squared is equal to 1. So that's the equation of this red circle here. And then the slice, we always put in a representative slice. This slice right here that goes all the way across the circle, this is the base of one of the rectangles, and it corresponds to this base right here, just so you get a visual and have an understanding of what part of that rectangle is sitting across the circle. They also tell us in this problem that the height of every rectangle that we create is going to be 3. So if we take our formula for the area of a rectangle, which is base times height, and we substitute 3 in place of height, we get 3b. That's where that comes from. So remember, we start with the geometry formula for the area of the shape that we're creating, and then we have to figure out over here, we already said this is the base of the rectangle. So what I'm going to do is I'm only going to measure the distance across half of the circle, and I'm going to double it. So if we take the equation of the circle and we get y by itself, because we are in terms of y because we're slicing perpendicular to the x-axis. I forgot to mention that. So y is equal to 1 square root of 1 minus x squared. That takes care of the top half of the circle. So yeah, there is a plus and minus, but I'm only interested in the top half of the circle. So the length of this black segment right here is from top to bottom. So it's the square root of 1 minus x squared minus 0. And then if I want the other side, the green part, I'm going to double that distance across, and that's where I get 2 times the square root of 1 minus x squared. And then when I multiply, and that's the base, and when I multiply that by 3, that's where I get 6 times the square root of 1 minus x squared. So this is my area formula for all of the rectangles that I'm going to be creating in my cake that I'm going to be making. The coefficient of 6 is going to come on the outside. My bounds are negative 1 to 1. I'm going to integrate the square root of 1 minus x squared. There's no square on that because we're not doing revolving, we're not doing circles. This is the area of a rectangle, and then with my calculator I get 9.424. All right, the next problem that we're going to look at is 3D. So let's slide this down and find 3D. Looks like it's on the next page. 3D is down here. Okay. So whoa. Let's see if we can get that sucker to work right. There we go. Alright, so in 3D, this was the problem. We've done one of these before with the same curves. And so in 3D, our curves are the upward opening parabola equation is y equal to x squared. That's the upward opening parabola, and I'll try to color code it for you. And the downward opening parabola is y equal to 2 minus x squared. That's our downward opening parabola. And in 3D, we are putting rectangles in, so we still need the formula for the area of a rectangle, which is base times height. And in this case, they're telling us that the height is equal to twice the base. So that's given in the problem. So I'm going to substitute 2b in place of h, as you can see right here. And then that gives me the area formula for these rectangles to be 2b squared. All right, now the base, I'm going to color that, is colored in this light blue color here. So this is one representative slice. We're perpendicular to the x-axis, so we are in terms of x. This is the base that I just colored. This is what's sitting across that kind of oddly shaped plate across both curves. And the length of that segment is going to be the top, which is touching the red parabola, minus the bottom, which is touching the blue parabola. So we're going to have 2 minus x squared. I'll write it here. 2 minus x squared top minus the blue minus x squared gives me 2 minus 2x squared, which is where that comes from. That's the length of the base, so I'm going to substitute that into my area formula. So that's 2 times parentheses 2 minus 2x squared quantity squared. That's my area formula that I'm going to integrate. My coefficient of 2, I'm going to bring on the outside. I'm going to put my binomial as the integrand. I'm going to square that binomial, which is what I did right here, and the bounds we found in the former video to be negative 1 to 1. If you set 2 minus x squared equal to x squared, you would x equal to plus or minus 1. That's where the bounds came from, the intersection points of the two curves. And this one I integrated by hand, but you can, if you do it with a calculator, you can divide that number, turn it into a decimal, and check your work. All right, the next we're going to do 4 through 7. So let me move my revealer, tools, revealer. All right, there's number 4, so I'm going to bring that down so we can focus on that. So in number 4, the base of a solid is a region grounded by the graph of y equals square root ln x, which is that graph right there, which you can produce on your calculator. The line x equal to e, this is the line x equal to e right here. Remember, e is 2.71 blah blah blah, so that blue line is cutting off the region where we're going to stop. And the cross sections are perpendicular to the x-axis, so we're going to be in terms of x, and we have squares. So the formula, we begin with geometry. The formula for the area of a square is a side squared. My representative slice is right here. Oops, I meant to change colors, but that's okay. So this is my representative slice, and that corresponds to the bottom of the square. So the length of the square is touching the top curve, which is square root ln of x, minus the bottom curve, which in this case is 0. So the length of the side is square root ln of x. I'm going to substitute that in place of s. So when I square the radical, that's going to give me, or lift the radical and give me ln of x as my geometry formula. So I could just say a equal. So I'm going to integrate. I am in terms of x, so I'm going to start at the low bound of 1. I'm going to stop at the high bound of e. So there it is, from 1 to e, ln of x, and you're going to use your calculator to evaluate that. Number 5, let's put my revealer in. I can do one problem at a time. So in problem number 5, the base of the solid is, and this is important, the first quadrant enclosed by the graph of 2 minus x squared. So here we have 2 minus x squared, y equal 2 minus x squared, and it says we're only interested in the first quadrant. If every cross-section of the solid perpendicular to the y-axis, so we are in terms of y, we're slicing perpendicular to the y-axis, is a semicircle. Danger, 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 danger. Semicircles are dangerous, 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 and watch and learn why. So if I put in a representative slice, and this is a semicircle, here's my slice going perpendicular to the y-axis, and it corresponds to this segment right here. And my slices will look like semicircles, as you can see. The formula for the area of a semicircle is pi r squared over 2. However, this pink, purplish, whatever color you call that, is not the radius. The formula needs the radius. Unfortunately, this is the diameter. So I only want half of that segment as my radius. So this black colored segment right here, that is the length of the radius. So when I find the length of the radius, I'm going to do the right side minus the left side, and then I'm going to cut that in halves because right minus left will equal diameter. Half of that's equal to radius. Now remember, we are in terms of y, so if I get y by itself, I get x equal to square root of, remember we only want the right side, y minus 2 divided by, so that'll be 2 minus y. So this equation of the downward opening parabola in terms of y is x equal to square root of 2 minus y. So the distance, so that's square root of 2 minus y minus 0 is equal to the diameter, and then I'm going to cut that in half, which is what I did right here, to get the radius. I'm going to substitute that radius in place of r. So notice what I'm doing is a slow step by step. This is r square. So if I square the numerator, it lifts the radical, and I get the 2 minus y. When I square the denominator, because I got to square the numerator and denominator, I get the 4. Then remember, I have a 1/2 right here. So if I multiply, if I bring the pi and the 1/2, there's the pi, and the 2 in the denominator times the 4 in the denominator gives me the 8. So that's where all of that comes from. I'm going to grab the pi and the 8 out as my coefficient. I am starting, remember we're in terms of y, so I'm starting at a low y value of 0 and a high y value of 2. In terms of y, from low to high. So from 0 to 2, there's my 2 minus y. I did this one by hand, and you get pi over 4. You can change it to a decimal in your calculator if you want to compare that. Number 5. Did I assign number 5? Because I don't have a number 5 here. Oh, that was number 5, duh. All right, number 5. Equilateral triangles. So in number 6, the base of a solid is the region bounded by the parabola x squared equal to 8y. So first of all, let's talk about the parabola. Over here, x squared equal to 8y. For our graphing purposes, we know we want y by itself, so I'm going to divide both sides by 8, and that just gives me 1/8 x squared equal to y. So it is an upward opening parabola with a vertex of 0, and my upward opening parabola here is in blue. All right, let's continue reading. Each plane section perpendicular to the y-axis, so now if I'm slicing perpendicular to the y-axis, I'm in terms of y. Remember, when you do your bounds, if you're in terms of y, it goes from low to high. Each perpendicular slice is an equilateral triangle. Oh, also my region is bounded by the line y equal to 4, which is my pinkish, purplish, whatever line up here. And this green segment is my representative slice. So the slice goes all the way across the region, so I'm coloring it right here. This is my representative slice of cake that I'm making on this parabolic shaped plate. And so here is the slice. So the segment that I colored up there corresponds to this segment right here. Remember, this is an equilateral triangle, so all 3 sides are congruent, and you need to go back. This is a formula you might want to get stuck in your memory. It's the square root of 3 over 4 s squared. So I need the length of a side. The side goes all the way across. So to make my life easy, I'm going to find the length of one side. I'm coloring it in black right here. I'm going to find the length of this piece right here, and then I'm simply going to double it. So all the way across is a side, but I'm going to find half of it and then double that region. So that means I'm going to do the right side minus the left side, and we're going to need that equation back in terms of y, so I need to get x by itself. So from right here, I get x equal to, technically plus or minus, square root of 8y. I'm only going to focus on the right hand side because I'm going to do the right side minus the left side. So that would give me the square root of 8y minus 0, which is the square root of 8y. To get the whole side, I'm going to double that. So the length of one side of one equilateral triangle is 2 square root of 8y. The formula says I need to square the side. So if I square 2, I get 4. If I square the square root of 8y, I get 8y. It lists the radical, and that's where the 32y comes from. So then I'm going to bring the square root of 3 over 4 into the picture. There's the square root of 3 over 4. So I bring in the square root of 3, and then 32 divided by 4 right here is 8. So that is the formula, the area formula that I'm going to be integrating. 8 square root 3, of course, is my coefficient. I'm integrating y from low to high. So my low y value is a 0. My high y value is a 4. And then you can see the integration and the solution. And then finally, number 7. Let's get rid of this revealer. Boom, gone. Let's drag this down. Okay, so in number 7, we have it's not the same parabola. This time the equation of the parabola is x squared equal to 4y, which is y equal 1/4 x squared. An upward opening parabola with a vertex of 0. Each plane section perpendicular to the y-axis, so we're in terms of y again. And those slices are squares. So one representative slice is right here, all the way across. So that corresponds to this segment right here. So this is the length of my side. So I'm going to do what I did before. I'm going to find the length of this piece right here. And then I'm going to double that region. So that would be a right side minus a left side. I'm going to get the equation in terms of y. So x is equal to plus or minus square root of 4y. I can take the square root of 4 and get x equal to plus or minus 2 square root of y. So the distance from here to here is 2 square root of y. I'm going to double that to go all the way across, and that's where I get the 4 square root of y. The area formula is side squared, so I'm going to take that side and square it. So 4 squared is 16. Squaring the radical gives me the y. 16 is my coefficient. I'm integrating y from low, 0, to high, 2, and you can see my work. So that's the workouts of the volume problems.